Welcome to lesson 57. In this lesson, we'll be solving exponential and log equations using the properties that you learned in the previous lessons. So other than all of these properties that we have seen so far, there is one other trick that we can try to confirm before moving on to solving equations. So here, let's take a look at the show question. Log x base a is equal to 1 over log a base x. So what can we do here? Well, I'm going to actually start from the right-hand side of this expression. 1 over log a base x, and apply a change of base formula to it. So I can write this as 1 over log a over log x. And when I take 1 over a fraction, what it actually does is to reciprocate the denominator here. And so by the change of base formula, I can reverse log x base a, which looks like the left-hand side. Okay, so this will come in handy in the next example that you're going to see. Okay, let me make it smaller and let me make it bigger again. So here is example 1. Solve and remember to check for extraneous roots. So in this question, we have log x base 3 minus 3 log 3 base x, which is equal to negative 2. So right away, you will notice that that property that we've just proven will come in handy. And I'm going to write the second term as 3 over log x base 3. So that now I have two terms that involves log x base 3 equals a negative 2. In order to avoid fractions, we can now multiply every single term by log x base 3. When I do that, I notice, well, the first term actually turns into a quadratic. So I'm going to bring that negative 2 to the left side. Don't forget to multiply by log x base 3. When I multiply the remaining term by the same thing, I get just negative 3 equals 0. Do you see a quadratic pattern here? If you don't, you can let a to be log x base 3. Then you're really looking at a squared plus 2a minus 3 equals 0, which allows you to factor into a plus 3 times a minus 1 equals to 0. So now I can say that, well, a plus 3 equals 0, or a minus 1 is equal to 0. If I back substitute log x 3 as a, I get this expression, or log x base 3 is equal to 1. Solving for x, 3 to the power of negative 3 is 1 over 27, or 3 to the power of 1 is 3. After you find these values for x, you should look for extraneous roots by substituting these values back into the original question. Well, since both x's are positive and greater than 0 and not equal to 1, it will satisfy the original equation. So we can say that there are no extraneous roots. And therefore, indeed, the value of x can either be 1 over 27 or x is equal to 3. Question B. Here we're subtracting logs, but these logs have different bases. So I can't just say, well, we can divide, the x by the x because they don't have the same base. Instead, I'm going to make use of the change of base formula. And it would be convenient if we keep, say, the smaller base here, the 25, and rewrite the second term as log x over log 625 of any base. Well, since we want to be able to combine any terms with x, a convenient base to choose this time would be 25. Let's see what this simplifies into. So I have log x base 25 minus log x base 25, and I can actually simplify because 625 is a power of 25 power of 2. That's what we have. And so we have like terms on the left side. 1 minus 1/2 of log x base 25. This simplifies into 1/2 log x base 25 equals to 3. I need more room. This is log x base 25 equals to 6, right? You multiply 3 by 1/2. And so x is equal to 25 to the power of 6. This is not equal to 1. This is greater than 0. So when I check for extraneous roots, it's fine. So this is an okay solution. Question C. Oh, good. This time I'm adding 2 log of base 9 together. So it seems like we can simplify this expression by multiplying x minus 5 and x plus 3 using the product law of log. So here we have log base 9 of x minus 5, x plus 3 equals to 1. I can change this into exponential form. 9 to the power of 1 is equal to the product of the binomial. I'm actually going to expand. So x squared minus 2x minus 15. Bring the 9 over, and we can now solve a quadratic equation. So we have x squared minus 2x minus 24. Factor this into x minus 6, x plus 4, which gives us x is equal to 6, or x is equal to negative 4. Now, don't be too happy yet, because don't forget to check for extraneous roots. We'll start with 6. If I substitute 6 as x, 6 minus 5, positive. 6 plus 3 is positive. This is okay. How about negative 4? Negative 4 minus 5, negative 9. This is not okay because I cannot log a negative number. So I'm going to write down extraneous root. And as a result, x is equal to 6 is the only solution to this equation. Next, we are going to look at some exponential equations. 2a, 2 times 16 to the power of x plus 13 times 4 to the power of x minus 7 is equal to 0. So I can see that, well, 16 to the power of x, I can actually write this as 4 to the power of x squared. If I do this, technically, I have another quadratic form. Because this is like 2a squared plus 13a minus 7 equals 0. So if we skip that step of, substituting a and back substituting, if you can see beyond that, we can actually factor this as 2 times 4 to the power of x, and then 4 to the power of x, and something that makes up to negative 7, and a sum of 13. So what would that be? So this is minus 1 and plus 7. So now I have two linear equations, or linear looking equations. right? And then we can make use of that to solve for 4 to the power of x. So in the first equation, I can put 1 on the other side, divide by 2. Now 4 to what power? It gives me 1/2. Well, first I know this there is a reciprocal, so that must be a negative exponent. And then 4 to the power of 1/2, the square root of 4. It's 2. So here we go. What about the second equation? 4 to the power of x is equal to -7. Is it possible? And the answer is no. So this side here, we have no solution. And the only possible solution is x equals -1/2. Second question here, 2b. We have e to the power of 2x plus 1 minus e to the power of x minus 1 equals 0. Well, e to the power of x, e to the power of 2x seems like some quadratic form here. But how do we deal with that plus 1? Well, this is, if we kind of think backwards, this is like multiplying e to the power of 2x times e to the power of 1 based on exponent laws. Does it make it better? If it still doesn't make it better, then I'm going to let a equal e to the x. So that here I have e as a coefficient times a squared minus a minus 1 equals 0. I don't want to factor this. So let's solve for a using the quadratic formula. So a is equal to negative b, so negative of -1 plus or minus b squared minus 4 a c. I'm going to flip the c and a, all square root over 2e. This is a monster. So at least clean this up slightly and write this as 1 plus or minus the square root of 1 plus 4e over 2e. Well, our goal is to solve for x, not a. So now we can actually back substitute and also use your calculator to work out the values of 1 plus square root of 1 plus 4e over 2e and then the minus version, okay? So here, e to the x is either equal to negative 0.44986 ... or e to the x is equal to 0.81774 ... From your calculator, we know that in order to get x, we need to ln both sides of these two equations. But e to the x can be negative, so there's no solution on the left here. But here on the right, x, so let's try this again. X is ln of 0.81. And keep in mind that you should keep all the digits on your calculator and only round your final answer when you are writing it down. And if nothing is specified, you round to 3 significant figures.